Hello, my name is Sergio Novaes. I am the PI of the SPRACE project, and I would like to introduce you the demonstration that we are going to do using the Bella link and take as a case the high energy physics data transfer. First of all, I would like to thank everybody that helped us to put this demonstration together, from Giant, FCCN, Rede Clara, RNP, HED-NESP, and PADTEC, and the institutions SPRACE, CERN, LIP, UNESP, and the INCD from Portugal. First of all, believe that high energy physics is one of the best cases to show the amount of data that should be transferred between different points in the world in the whole realm of e-science. We have nowadays the most prestigious accelerator is CERN that runs the LAC. We have 4 experiments. 2 of them are multi-purpose like Atlas and CMS. And in this 27 kilometers ring, we collide proton versus proton that are measured by these 4 detectors. Just to have an idea, the size and the dimensions of a detector like that, I'm taking CMS, and you can see that we have kind of 12,000 tons of weight and 21 meters long detector. Okay, to have an idea how big it is, I put an arrow here, a yellow arrow pointed to a human being here, close to the real stuff, the real detector in the cavern. That's almost 100 meters below ground. This kind of collisions produces a lot of data. What I mean, you have proton bunches colliding every 25 seconds. We have 150 million sensors delivering data. You have more than 30 petabytes of new data per year, and all data must be distributed worldwide. And this is an event. There are simultaneous, let's say, what you call pile-up events in a single bunch crossing. And this what we have in the detector itself. This data has to be distributed, processed, stored by different sites in the world. We have created infrastructure, what you call WLCG, Worldwide LHC Computing Grid infrastructure, that's now counts with more than 107 sites from 40 countries. We have more than 300,000 cores, 500 petabytes of storage, 2 million jobs by day, and with links that goes nowadays up to 300 gigabits per second. How is let's say, the structure of this processing power? It uses the grid architecture to mount a grid infrastructure. As I said, when you have a tier 0, that's at CERN, and we have constructed another mirror of the CERN infrastructure at Hungary. And as a tier 1, we have several countries that contribute for this level of processing. And as the last level, we have the tier 2s. Here is SPRACE, and here is LIP. and they are connected to a specific tier one. In the case of sprays, we go to Fermilab. In the case of LEAP, they are connected to Spain. And we try to make two demonstrations with the Bella link. One of them is connecting the LEAP in Lisbon to the sprays via grid FTP transfers. And we are going to make an experiment with CERN using Russia. Just to have an idea of the amount of data, this is a little bit outdated because we changed the way we transfer data from FedEx to Russia. But this is what you have done of the amount of data that goes to space and from space as until 2019, okay? We have 9 petabytes to space and 3 petabytes of data from space from all parts of the world. To have an idea, our production nowadays is established to make a priority the link with Fermilab. So we will leave space here in the South America, goes all the way to Miami, from Miami to Atlanta, Washington, D.C., London, Paris, Geneva, and come back to Portugal, okay? The latency of this link is 254 milliseconds. And when you try to do the same connection between sprays and LEAP in Lisbon, we have now available for us the Bella link that goes from São Paulo to Fortaleza and to Fortaleza to Lisbon, direct link of 100 gigabits per second with a latency of 106 milliseconds, okay? If we already have a big amount of data being transferred, with the project of the high luminosity LHC, this amount of data is going to grow significantly. We are going to need, by the middle of this decade, more than 20 times the CPUs that we have right now, and we are going to need disk to store the data around also 20 times what we have available nowadays. So high energy physics is demanding a lot of distributing, processing, and storage of data. And for us, the links, the grid concept just work when you have a very good and very fast link to connect all the sites. And we have a strong need right now, and this is going to be even stronger in the future because of the high luminosity, what means that the amount of data, amount of protons that are going to collide by each bunch is going to be larger, and we have more events in each bunch crossing. Thank you, and I would like to hear now from LEAP that they're going to present their infrastructure over there. Thank you.
My name is Jorge Gomes, and I'm a researcher at LIP in Lisbon. Let me introduce you to LIP and to the importance of Bella for the LIP research activities. LIP is the Portuguese High Energy Physics Research Laboratory, is the reference organization for experimental particle physics and associated technologies in the country. LIP participates both in ATLAS and CMS, the two largest LHC experiments at CERN, and also participates in a wide range of other experiments, both at CERN and at other research laboratories in Europe, North America, and South America. LIP also has research and development in detectors and instrumentation, and performs research towards application of high energy physics technologies and techniques to healthcare, space, and information technologies. Finally, LIP has a strong activity in what relates to society and outreach. Several of the LIP activities bridge with Latin America. Examples are the participation in common experiments, such as the LHC experiments at CERN, participation in the OG experiment located in Argentina, development of the Marta detector with Brazil for the OG experiment, participation in the upcoming Dune experiment at Fermilab in the US, and development of the Southern Wide Field Gamma Ray Observatory, aimed to be deployed in the future in South America. What do we do in high energy physics? Well, we explore what the world is made and how it works. And we do so by creating scientific experiments that are so complex that require international collaboration. Information technologies are essential both for that collaboration and to perform the data access, processing, and analysis at a global level. That's why the World Wide Web was created at CERN, to enable information sharing between researchers regardless of their location. Computing is also an integral part of the LIP activities, and one of the spin-offs that is important for this Bella demonstration is INCD, the Portuguese National Distributed Computing Infrastructure, that leverages the LIP experience and expertise in scientific computing and data handling. The Portuguese Tier 2 computing facility, integrated in the worldwide LHC computing grid, is a partnership between LIP and INCD. The increase in luminosity at the Large Hadron Collider in the upcoming years will be a huge challenge for us. The data volume and compute storage and data transfer capacity required by WLCG will increase dramatically. And the network is one of the parts of the puzzle. And that's why Bella is so important for us and for particle physics research in Portugal and Brazil and elsewhere. So welcome to the high energy physics data transfer demonstration using the Bella network link. In this demonstration, we'll show you how Bella will support the high energy physics community in the forthcoming years. So just as a reminder, the worldwide LHC computing grid is structured as a set of tiers that include several computing facilities in each tier. So the experiments produce data at a huge data rates, and this data is sent to the tier 0 at CERN. And then we have a set of tier 1s, large tier 1s that have data custody across several countries. There are 14 tier 1s. And then data is distributed to the tier 2s. The tier 2s also provide computing capacity for simulation that is then stored in the tier 1s. So the data transfer between the several tiers is of utmost importance to us. In the demo, we will show the data transfer between LIP and SPRACE. So these are two tier 2s, one in Portugal and another one in Brazil. And we will be using grid FTP and the worldwide LHC computing grid tools for the data transfer. So grid FTP is one of the data transfer protocols that is used by the high energy physics community, namely in the worldwide LHC computing grid. And in the demo, we'll discuss the aspects of network data transfer, the bandwidth and latency that affect the data transfer. And then we'll show you the location of data sets. We'll be performing data transfers, and we'll show you the results as measured by our monitoring tools, both at SPRACE and LIP. So let me just give you some words about the LIP setup. At LIP, as it has been previously explained, the tier 2 is in fact hosted at INCD, the Portuguese National Distributed Computing Infrastructure, that provides the computing and data resources to support the tier 2 and other research communities in the country. And for this demo, we set up two servers, Bella 1 and Bella 2. With each server has a network interface card with a capacity of 100 gigabits bandwidth, so 100 gigabit Ethernet, and it's connected to a Cisco Nexus switch, both servers, and these servers are then connected through a dedicated link to the Portuguese Academic Research Network, which is FCCI. Actually, the equipment, network equipment from FCCN is already hosted within the same data center where the tier 2 is located, which facilitates the network connectivity. And then FCCN is connected to GN, which provides the connectivity to Bella. So looking at the network latency between LIP and SPRACE before Bella and after with the dedicated links for Bella. Previously, we had a 255 millisecond round trip. And you can see here the trace route between our tier 2 and the SPRACE tier 2 in Brazil. And you can see that we had 18 hops in the trace route previously, and now we only have 8 with Bella, and this provides us a 106 more or less millisecond round trip. And now I give the word to SPRACE.
So, hi. So I'm Rogério from the Center for Scientific Computing at São Paulo State University in São Paulo, Brazil. We also operate tier 2 cluster, which is tied to the CMS collaboration. If you go to the next slide, please. Here we can see a bit of the setup that we have configured for this demo. So we see the SPRACE as a tier 2 center, which is inside the São Paulo State University. We are responsible for the scientific computing data center of the university. So SPRACE is installed inside this data center. We have also prepared 2 servers, SPRACE 01, SPRACE 02, tied with inside our infrastructure using 100 gigabit per second network cards. So our setup includes 2 Huawei switches, one installed in our data center, the C8861, and another one installed at RedNesp. RedNesp is a regional research and education network. The acronym stands for Research and Education Network of São Paulo. So it's more or less 30 kilometers far from our data center. So we have some optical equipment to connect these 2 switches. For this demo in particular, we connected to RNP, which is the national RNE network, Brazilian RNE network. And so we connected at 100 gigabit per second at the Cisco ASR 9000. And from RNP, we can reach Red Clara, going from São Paulo to Fortaleza, also in Brazil. And from Fortaleza, we get the Bella link up to Lisbon in Portugal. Our production traffic goes through US. So we go the other side of the picture, going through Light, which connects us to Miami in US. And from there to Atlanta and Washington, DC. So we get Internet 2 and SNet, and from there we go up to the tier 0 center at CERN. So next slide. We see in this diagram already shown by Sergio before, the difference in latency when we go to Lisbon from São Paulo, going to our production network that we have nowadays, and the new link provided by the Bella link. And we can see the big difference in latency that we can get from this new path, which is quite interesting to us. The next slide. I don't think there's another one. Oh yes, and this is a plot showing the results that we've been getting from almost 1 day and a half before up to today, showing the several transfers using different tools, showing the traffic using the Bella link. So I'm here at Sprays access machine, and I'm starting a trace route through Bella 1, which is in Lisbon, and we see from our production network that we have this 254 milliseconds, starting from our gateway up to the machine in Lisbon. And if I do the same from our machine in our data center, but tied to the Red Clara, so we're using the new path that we have just established, and we do the same trace route, then we got the value that we shown before, 107, 8, 10. Best result should be 106 milliseconds. So now we see data transfer demo running in real time. We've started this transfer a few minutes ago, and it's quite stable, going more or less near 100 gigabit per second limit of the link. This transfer is going from Sprays. Data is being generated at Sprays and being sent to Bella in Lisbon. So we see that it's quite stable. The average transfer around 8, 9, or 90 gigabit per second, and we can sustain this traffic for quite a long period, which is a very good result. We consider this a very good result.
So now we'll be demonstrating usage of grid FTP to transfer files between Sprays and the LIP tier 2 in Lisbon. So we'll be using grid FTP between the production systems of the tier 2 in Brazil and the tier 2 in Lisbon. And this will enable us to see the current status of data transfer from the production systems using not the Bella cable, but the production connection that in case of Sprays goes through the US as it was before explained. So I will fire a data transfer. We can see that we'll be transferring a 1 gigabyte file from Sprays, from the storage resource management system at Sprays, and we'll be using GFAL, which is a tool used by WLCG to copy files. And we can see here the endpoints for the file transfer in Sprays. So we are using the production systems in both ends, which are SRM systems. And as we can see, we are transferring at 34 megabytes per second. A file with 1 gigabyte size. And we achieved 34 megabits per second, and the transfer is finishing 30 megabytes per second. So about 240 megabits per second for 1 gigabyte file transfer. And now, transferring 2 files. So I will be using 2 windows, each one with a different file transfer. And these files are 40 gigabyte files that are also at servers in Sprays. 2 servers, Sprays 01 and here Sprays 02. And they are being transferred to Lisbon. And at this moment, the file transfer is being set up for this file transfer. So the file transfer started. for both file transfers. We are transferring at 578 megabytes per second, and here at 600 megabytes per second. So this is a 40 gigabyte file. In production, we transferred a file with 1 gigabyte. As you can see, the bandwidth is quite constant. And it finished in 94 seconds here and in 96 seconds here. And the file, you can see the file already in the storage system in Lisbon with 40 gigabytes. And the same here. So let's see. We need to wait a bit for the monitoring. And we can see here the aggregated usage of the Bella link for the tier 2. And it's a 10 gigabit per second, a 10 gigabit per second transfer, which is a considerable improvement over the production. So now we'll be demonstrating the transfer of multiple files, not only 2 files in parallel, but a considerable number of files in parallel between Sprace and LIP, and using the same technologies. And I will fire these transfers. We'll be using the SRM storage systems at Sprace and LIP still, and using grid FTP, but this time with a considerable number of transfers going in parallel of different files. So we'll be transferring between a pair of servers files with a size of 10 gigabytes. And between the other pair, we'll be exchanging files also with 10 gigabytes. And as we can see, we are achieving a transfer of a bandwidth of 46 gigabits per second, transferring files from Sprace to the LIP tier 2.
Hi there, my name is Katie Ellis. I work at the Rutherford Lab in Oxfordshire, United Kingdom, and I'm a member of CMS. Today I'm going to show you how to make a transfer from CERN to Sprace in Brazil. So firstly, I need to find an appropriate data set to do the test with. And I found this particular block here, which contains 2 files and total size of 1.7 gigabytes. So I'm going to take a copy of that and check using Rusio, which I've already set up. This is our data management tool. And I'm going to look at where this block is placed already. So this is telling me that the 2 files in this block are based at KIT, at CERN, in the US, in Russia, on Fermilab tape, and in Italy. So now I'm going to place the rule which will move the data from CERN to Sprace. Here I'm specifying the site in the CMS site naming convention. And now I'm going to specify the source. Which is CERN. This should be all we need to create the rule. And now it's been successfully created. I'm going to check that it all looks good. So check the rule info. And there it is. So it's in the replicating status. That's good news. Now I'm going to look at the names of the files that we've just asked to be copied. Here are the two names of the files. They are root files. And I'm going to use this full name to search in the Kibana monitoring and see whether our file has been submitted. And I can see that it has been submitted. You can see the destination RSE is Sprace. If I make this a little bit bigger, maybe it's easier to see. So you can see there are two elements here. The first one was the queued transfer. The second one was the submitted transfer. And we'll come back in a little while to see the transfer being made. And we're back, and I can see that the transfer which was submitted earlier between CERN and Sprace is complete. Here it says transfer done. And we can check in Rusio that this has been completed. And indeed, you can see that the rule is now in an okay state, and I would expect to find those two files on the disk at Sprace.